At Solar Energy International in Carbondale, Colorado, Johnny Weiss and his partner Ken Olson teach the practical use of renewable energy technologies. Johnny has been teaching, designing, and installing solar electric photovoltaic systems for the past 15 years.
There's 5 major components to any PV system. The first is the collector, or the solar array, the solar photovoltaic modules. This is what collects the solar energy. The second component is some type of power conditioning equipment, some type of controller like we have here on the table that's going to condition the power. The third component is some way to store the photovoltaic solar power in the form of batteries, battery storage. Another component is an inverter that changes the DC power in batteries to alternating current so we can conveniently use our conventional appliances. But perhaps the most important component in a PV system that determines the size and the scope and the cost of solar energy systems is what we call the loads. The loads are the end-use electrical equipment, the lights, the pumps, and all of the appliances that we need to run. This package over here is a complete photovoltaic system. It's got all the components. It's got a collector to charge up the batteries. It's got a controller to prevent the batteries from being overcharged that's built into the equipment. It's got a battery in here to store the power. And it's got an end-use light so that we can have power at night, solar power at night. This is a complete example of a photovoltaic package. In addition to the 5 major components, we've also got safety equipment that is essential to the safe performance of PV systems. On the board over here, you'll see disconnects and fuses and different pieces of equipment that are required by the National Electric Code to make our home residential systems safe and code complying. Photovoltaic modules come in a variety of sizes and types. We feel the most important thing in selecting the module that you're going to use is to concentrate on who you're going to be buying it from and what type of service you're going to be getting from the dealer, because most of the commercially available modules that are out there perform very much the same. And the type of service you're going to get long term is a very important component. These are quality pieces of equipment that get shot into outer space. They're going to be producing power when most of us are long gone. They're really very dependable, so who you buy it from is really most important. The basic parts of a PV system, the major system components, are very dependable. Where PV systems get into trouble and where we have maintenance and operations problems is in the wiring between the components and particularly in the connectors. Using the right terminal ends and making the right connections is what really makes PV systems sustainable for years and years. Let's talk about one of the most important connections, and that's the connection right in the module junction boxes to the wire that's going to run from the solar collectors down to the power conditioning equipment. This is a number 10 copper wire that's rated for outdoor use, so we can use it outside. Having the right tool to strip number 10 wire properly without damaging any of the copper strands is real important. Likewise, having the proper connector to go onto that wire is real important. This is a number 10 spade terminal that's the recommended connector for this particular photovoltaic module and this particular wire. We want to do a crimp connection, which is a mechanical connection. This is what's going to hold it on there. Using a good crimping tool is a big help. That's a good, strong mechanical connection. One way to improve this connection would be now to remove this little insulated piece and solder this connector to the wire as well. Soldering takes some time, but it's worth it when we're looking for a 20-year connection that's going to be hard to get to and maintain. A soldered connection means that there's going to be less resistance. There's going to be more surface area, more contact for the electrons to flow. It doesn't help structurally. We still need a mechanical crimp connection, but the solder adds more surface area. In this case, we're not going to do that, but what we're going to do is provide some heat shrink. This is a way to reduce the possibility of moisture getting in here. And of course, moisture is what causes the corrosion, and the corrosion is what ultimately makes a break, and we have an open circuit. Electrical tape will work, but heat shrink works really well too. Let's go ahead and fire up the torch and melt this heat shrink right around this connector. These heat shrink products have a little bit of glue on the inside, so we want to carefully melt the heat shrink so that it'll wrap around and that glue will melt and create a real good seal all around the It's done, it's ready. The connections inside the junction box are real important. It's nice to leave a little extra wire just in case. And now we can take our proper connections and put them in the right spot. Red is positive and black is negative. And we make it look nice and neat inside there. And now we shove the wire in so that this strain relief clamp is going to tighten up on the cable itself and not on the individual strands, not on the individual conductors. So we'll tighten this up. And that tightens the clamp, and then this tightens it on the wire. And it prevents moisture from getting inside. Now, our critically important connections we want to make with the right tool. And we want to torque these down with a nice, even, steady pressure. And make a good 20-year connection. Inspect it one last time. And then close it up. PV module performance is affected by three things primarily. The first one is orientation. The second one is tilt angle, and the third is shading. Let's start with orientation and this pump and the bucket demonstration here. We're going to do some direct pumping of some water with this photovoltaic module here. And you'll see as I orient the module, as I turn it toward the sun in relationship to its east-west azimuth, the module produces its most power when the module is facing directly toward the sun. Likewise, with tilt angle, if we tilt the module away from the sun, module performance is reduced and we get less water flowing. As we slow the module down and there's very little light shining on the module, we stop the pump from working. As we tilt the module up, the water increases until we're able to get the maximum out of this module and this pump at this tilt angle. Basically what we're trying to do is to provide an opportunity for the sunlight to strike directly into the photovoltaic module and not be reflected off. Our third issue is the effect of shading. As we shade the module, it's going to dramatically reduce the current output and therefore the water output of our pump. You'll see that just a shadow across the cells like this shuts the pump down. There's no effective current flowing from the module with just this amount of shading. That's why preventing shading is critical to PV system performance. There are some rules of thumb we follow for mounting PV modules. Number one, we want to keep them unshaded from 9 in the morning to 3 in the afternoon throughout the whole year. Number two, we want to face them at the optimum orientation. And in northern latitudes, that's any place above the equator, we want to face our modules true south, where the sun is in the sky at solar noontime. And our third rule of thumb says that we should mount the modules at a tilt angle equal to our latitude for best year-round performance. If we want to optimize performance for the wintertime, we do a latitude angle plus 15 degrees. If we want to optimize our array for summertime use, we put it at latitude minus 15 degrees to take advantage of the sun being higher in the sky during the summertime. This is an example of one of the simplest ways to mount PV modules. We can do them on the ground or we can do them on the roof with simple angle iron technology. This is very, very reliable. It also provides easy access for maintenance, and it's also a way that we can easily expand the array when we need to. And it's just proven as a good way all around. One of the potential problems with this array here is that you can see there's some shadow starting to happen just at the very bottom of where we've temporarily mounted this array. And that shadow is coming from the trees. And as the sun gets lower in the sky in the wintertime, those shadows are going to creep up and cause a severe shading problem on this module unless we're readjust the whole structure here. Another way to deal with shading problems is to go ahead and mount the array up on a tall pole like we have over here. With this type of mounting system, we can get above shading problems. We also reduce the potential of any theft or vandalism problems as well. These pole mounts are tilt adjustable, and they can adjust on the pole as well so that we can orient the tracker or the top of pole or side of pole mount to take advantage of the right orientation and tilt angle that we want for a specific system. This mount here on the top of the pole is a really important place to talk about maintenance issues. This is why we have to make strong connections. This is why we have to make electrical connections. They're going to last for 20 years. It's very difficult to get up here and check this mount. We do request and suggest that homeowners do that on a regular basis, but it's a very hard thing to do practically. That's why these top of pole mounts, while they're excellent for getting the array up in the sun, they also provide some maintenance, troubleshooting difficulties if it's hard for the homeowner to get up here and check things. What we have in front of me here is a passive tracker. It follows the sun in orientation on a momentary basis, daily basis across the sky. It works by the shifting weight of a refrigerant that is in a closed loop installed permanently inside of the actual frame of the tracker itself. In the morning, it faces the sun in the east, and as the sun moves across the sky, it warms up the fluid and drives the tracker without using any energy, simply passively by natural energy flows. It moves the tracker by gravity fundamentally over to the west where it takes advantage of the late afternoon sun. This type of tracking system is a wonderful system when we're looking at trying to get more energy out of our PV modules during the summer. Typically, we use this when we're dealing with agriculturally based systems, irrigation and water pumping, whether it's for livestock or for agriculture. These trackers make a lot of sense when we're pumping water during the summertime. They do have some minor drawbacks though. They do cost a little bit more, and they do have a few moving parts. They have this shock absorber here in the middle, and that's designed to prevent the unit from racking in the wind. They're tilt adjustable, so we have to go up and adjust it for its tilt angle, even though it adjusts itself automatically for its orientation. But tilt angle adjustments are very easy. We can make those just 3 times a year, and we're covered in that regard. Another consideration is windy environments. Trackers work best where they don't have to deal with constant or very regular strong winds. This is a different type of tracker. It's more mechanical. It works with satellite dish technology fundamentally. It's also very reliable. We've had very good luck with this tracker, and it's been out for quite some time now. It follows the sun in both axes. It follows the sun on a daily path across the sky, and it also tilts automatically to follow the sun seasonally. It's the 2 actuator arms, the long handles you see here, that push the tracker and drive it where it needs to go. There's one that adjusts it for tilt, and the other adjusts it for orientation, so that this tracker should always be following the sun or the brightest spot in the sky. It decides where that is based on a photocell that is installed at the top in a little control piece of equipment. What we're doing out here on the site is trying to analyze this site for its solar access. We're trying to decide where's a good spot to put the solar array, that it's not going to be shaded. So we've got an instrument called the Solar Pathfinder, which is a wonderful device that enables us to take one glance at it, and we can tell what shadows are going to occur on this particular site every hour of every day of the year. Let's take a look. It's got an adjustable tripod so that we can set it up on an angled roof if we need to. This is a professional's tool. We don't recommend that homeowners buy this just to figure out where to put one particular array, but hopefully an installing dealer has access to this kind of equipment, because it takes all of the mystery, all of the guesswork out of deciding whether this is a good site for solar or not. We're going to measure several spots around here, and then we can very easily decide which one's going to meet our most important need, and that's to keep the solar panels in the sun from 9 to 3. 9 in the morning to 3 in the afternoon is great for us. The instrument's got a compass on it, so we can adjust for orientation. It's got a bubble in here, a level, so we can adjust for establishing the horizon. And with those 2 reference points and a sun path chart that's for our particular latitude, because it's our latitude, it's our place on the Earth relative to the equator that determines the path of the sun. So we've also got the months listed here and the hours of the day, and it's a little confusing to look at it first, but after a little bit of practice, it really works great. So I'll set it up on here. I now orient it so the compass is facing magnetic north and magnetic south, and I tilt it so the bubble is right in the middle, which means that the instrument is level. And then I set the optically correct globe on top so that we can look at the reflection of anything that's going to appear in our solar window at this particular site. It's a very site-specific tool. It's analyzing this site right here for its solar access. What shading's occurring here? If we move it 10 feet in either direction, or just a few feet in either direction, or up and down, we're going to get a different reading, because that's a different site in relationship to the objects, to the trees, to the buildings, and so forth that are in our view right now. You can see my reflection in the bubble. You can also see the trees over here. And we can see the hours of the day running across the bottom. My finger's pointing at 12 noontime. That's solar noon. We can see that at this particular site, we're going to have a little bit of shading from this tree in the morning hours. And in the afternoon, over here, there's no shadows. So, with one glance, we know what's going to happen every hour of every day of the year. If we move over here directly behind this tree, we can see that this is not at all a good site to put any type of solar collector, because the collector would be shaded throughout the morning every month of the year except for June. But when that tree grew up a little bit, it would be a shading problem in June as well. We've got no solar access problems on this side, but we do have considerable shading over here on this side. Another consideration we have to deal with besides shading in mounting PV arrays is the issue of line loss or voltage drop. When we move these arrays far from power conditioning equipment, when our batteries and our control equipment is way over there in the biodome and the array is out here in the field, we have to be very careful to make sure that we've got the right size of wire as well as the right type of wire to bring all of this power into the power conditioning equipment. So we have to look on charts, we have to calculate, and we have to select the appropriate wire size. That's one of the most common problems we find with owner-done systems, homeowner-built systems, is that they don't use the right wire between the array and the power conditioning equipment. Many people want to know whether it's possible to reflect more light onto PV panels and therefore get more output from them. It's a good question, and it's true. If you reflect more light on the panels, you'll get more amps of current flowing out. The problem is that they're not manufactured with that in mind. There are commercially available concentrator and reflector systems, but we want to caution people about building their own type of reflecting system. As you can see here with this one that's been in Carbondale, Colorado here for nearly 20 years, it's still working, it's still putting out its rated power, but you can see the browning that's occurred here. We've damaged the module here because of the extra heat. Yes, it will produce more electricity if you reflect or concentrate light on them, but these modules weren't designed for that. You really have to be very careful not to install it like this, because the heat can damage the module, and it's not worth damaging the module just to get a little bit of more current out of it. The fundamental purpose of a charge controller is to prevent the batteries from being overcharged by the solar array. In addition to that, charge controllers can be very sophisticated and they can do a lot of other important things for us. Often charge controllers come with some type of light, indicator light, and some type of meters so that we can monitor battery state of charge, how much power is coming from the array, how much power we're using in our appliances. Charge controllers are usually the place where most homeowners interact with their system on a regular basis. These charge controllers here are some of the state-of-the-art that's available today. These controllers are very sophisticated. We've got field adjustability on these controls. These are controls that we can adjust depending on the type of batteries we use and how we use energy in our PV systems. These controllers allow us a lot of flexibility once we know technically how to adjust them properly. We've also got features on here that can really make a lot of sense in terms of making PV systems more sustainable. This has a feature that we call equalization, which allows the array to periodically charge the batteries with a controlled overcharge. The equalization charge helps batteries last a long time. Determining the correct voltage for your PV system is a very important question. Our feeling is that 12-volt systems, which is the basic building block for the photovoltaic modules, for the batteries, for the equipment, 12-volt systems are most appropriate for smaller systems, for cabin-sized systems, for systems that are on recreational vehicles and motor homes and boats, and for the cabin that's used occasionally and on the weekend. Once we get away from just small systems, once we need a home to be powered every day, 365 days a year, then we're really looking at a larger type of power system. And 24-volt systems make a lot of sense for those applications. For residential homes, our recommendation is to go ahead and start right off with a 24-volt system. This component, the inverter, is the device that takes the DC and changes it to AC to run our AC appliances. Because these inverters have become so much less expensive, more efficient, and more reliable, it's really affected how we're going about sizing and designing PV systems now. Since they can put out a power that is cleaner and so efficient, we are not as dependent upon DC appliances as we used to be. DC appliances, the type of thing that plugs into your cigarette lighter plug, the type of thing that's in a recreational vehicle or on a boat, marine applications. We can use those as well if we'd like, but we don't have to shy away from using modern AC appliances because now we've got quality inverters. To get the best of both worlds and get AC out of the inverters and DC directly from the batteries, I think it makes sense to consider a hybrid system, a system where some of the appliances in the house are going to be run off of your inverter with your 120-volt AC system, and then some are going to be run off of the batteries and run directly on DC. If you're going to be running loads on AC, it makes sense, I think, to have as large an inverter as you can afford. And the larger inverters have more options and are typically available in 24 volts. So it's possible to have a hybrid system and truly get the best of both worlds. The storage component in a photovoltaic system is the batteries. It's the batteries that store solar power and allow us to run our systems, our photovoltaic systems, during cloudy weather, during times when there's no sun, and of course at nighttime. Photovoltaic storage batteries are very different from car batteries. Car batteries are designed to start large motors and then get recharged up by our cars very quickly. Photovoltaic batteries, storage batteries, are deep cycle batteries. They're like electric vehicle batteries, golf cart batteries, or forklift batteries, floor sweeper batteries. These are batteries that are designed to be discharged very slowly over a long period of time. And that's typically how we use our batteries in a PV system. We charge them up for a few hours during the day, and then we discharge them throughout the night. We also want to have storage capability for not just one evening of storage, but for several cloudy days at a time. And when we size PV systems, we select the number of days of autonomy that we need, the number of days of no sun that we want our system to work with, supplying our appliances with power without any disruption of power whatsoever. The batteries are the most labor-intensive and maintenance-intensive part of PV systems. They're not only heavy and hard to carry, but they also require some routine maintenance to make sure that they're going to perform to their maximum life. We can get 10 years out of many of these batteries if we treat them properly. If we abuse batteries and don't do the maintenance, we're going to have reduced battery life and therefore more costly systems in the long run. It's also very important from an environmental perspective to take care of these batteries and make sure that we recycle them and so forth when we're through with them. There are three basic things to remember when trying to maintain any type of battery bank. The first one is to keep tight connections. Tight connections allow for good conductivity of the electrons through the wires. We don't want to have resistance. We want low resistance connections, therefore tight connections. The second thing we want to do is to make sure that we have the proper electrolyte level inside the battery, a right amount of water. These are wet batteries and we need to keep them with the right amount of fluid. The third thing we want to do is to keep the battery bank as clean as possible so that we don't have corrosion and therefore loose connections as well. Those three things are really important to do, and the batteries require more maintenance than any other part of a PV system. Another important thing about battery maintenance is providing a periodic equalization charge. By an equalization charge, we mean a regular controlled overcharging of the batteries to bring all of the cells up to their proper specific gravity. In this case here, we've got a 12-volt battery bank. We've got it hooked up to this meter here, which is giving us a very accurate reading of battery voltage. Up at 16.5.6 volts. This means that the batteries are up at a full state of charge, and we're now providing a little bit of equalization charge to them to try and make sure that we're going to reduce any sulfation building up on the plates. This is something we want to periodically do with lead-acid batteries so that they'll last as long as possible. Whenever you're doing battery maintenance, it's very important to have some safety equipment. Eye protection is critical. Rubber gloves are real important. This instrument here is what we use to measure the specific gravity, the real state of charge of a battery. It's called a hydrometer. And we recommend that PV system owners use a hydrometer at least twice a year to test every cell in their battery bank, every battery in their battery bank, and make sure that they have a good equalization in the specific gravity of all those different battery cells. Let's go ahead and do a brief hydrometer test right now. It's important to remember to push the ball in before putting it down in here so you don't get any bubbling of this sulfuric acid. What you want to do is very carefully draw up the electrolyte, the fluid, the sulfuric acid solution up into the hydrometer. And then, without spilling any of it, you can read the reading and check the actual state of charge of the battery cell. This is the best and only accurate way to measure the state of charge of a battery cell. Using a hydrometer like this is the best way to check for a weak cell in a battery bank. Cells in a battery bank are kind of like horses in a team. If you get one horse that's dragging or one horse that's pulling too fast, doing a runaway action, it's going to affect the performance of the whole team. So you really need to check the hydrometer reading for every single cell to make sure that the batteries are working well together. Some of the other connectors that are important to get right are the connectors between the batteries and the connectors between the batteries and the inverter in an AC system. These are typically larger current-carrying wires, and we require some special tools to get these connections right and to work with this size of wire. This clippers here can make a nice clean cut. It takes a bit of effort, but we can get a nice clean cut. The next step now is to go ahead and trim this wire back, trim the insulation back, trying not to cut any of the copper conductors. One tool you can do that with is this sharp clippers. A connector like this is one of the ones that can be used to go onto the battery terminals themselves. These come in different sizes, and you need to get the right size lug for the right size wire. And it requires a special tool, a hex wrench, to go ahead and to tighten this. Likewise, the connector now has to be attached with as much surface area as possible to the lug coming out of the battery. This particular battery has it set up for this to go on this side, for the bolt to go through, and then we can tighten it up with the nut on this side. And before this gets tightened all the way, you can put some Vaseline or some anti-corrosion material on here if you want to. And then this should get tightened up real tight, and it needs to be checked periodically. Every 6 months is a real good idea. The energy coming in here from the sun through this cord here comes first into what we call a fused disconnect. We've got a way to disconnect this source of voltage from the rest of the electrical equipment so we don't get a shock. Inside here, we've got fuses, and fuses are required by code to protect the wires from overcurrent. It's overcurrent protection. So in this case, we've got what's called a single throw, double pole fused disconnect. Once the array power is disconnected and fused, the wires go over to the charge controller. They get to the charge controller by going through this box here, which we'll see in a minute. But the wires go up to the charge controller, and then the charge controller can do its job of regulating array power. The power comes back out and goes into the DC load center, back up here, and then over to the battery for array charging of battery. Let's take a look at it from the load or the appliance end of things. We've got a DC receptacle down here. This is typical bayonet receptacle for 12-volt DC appliances, the kind of thing you'd plug into your cigarette lighter plug. The receptacle gets its power through the DC load center, which also has a fused disconnect, or what we call a circuit breaker. We can have more circuit breakers if we have more circuits. But this is a way to disconnect this particular circuit, a very conventional type of system. The alternating current, the AC power, has to come out of the inverter. The inverter gets its power, 12-volt DC power, coming out of the battery, going into the inverter, being changed to 120 volts AC, and goes out to another AC load center in this case. And the AC load center is circuit breaker and fuse protection for the AC loads symbolized by this conventional AC outlet down here. The other piece of equipment you see here is a fuse. A inline fuse with a protective plastic cover on it. And we fuse the positive wire coming between the battery and the inverter, once again to provide overcurrent protection. On top here, we've got the electrical meter. This metering equipment enables us to monitor battery voltage, perhaps the most important thing we can do in terms of making sure that we know exactly what's happening with our battery bank. The other meter here is the array current meter, so we can measure the amount of amperage at any moment coming from our solar collectors. This simulates the procedure for installing the grounding system of a PV system. We want to have our green wires, our bare wires, which are non-current carrying wires, go to ground. That's standard electrical practice, and we install photovoltaic systems and renewable energy systems in very much the same way as we do conventional electrical systems. Providing a good ground is an important part of the safety features that we want to encourage everyone to participate in. Grounding the system prevents a shock hazard in case of a fault condition. So good grounding is just good electrical practice. This is a power center that combines a lot of the equipment that you saw in the other, at the other power board all into one box. This box has a big disconnect for safety that disconnects all sources of voltage at the same time. This is a UL approved piece of equipment so that state electrical inspectors don't have any problem with it whatsoever. It's got DC loads, DC load circuit breakers here, so we can have a variety of, so that we can have several DC appliances like energy efficient 24 or 12 volt refrigerator, lighting circuits, kitchen circuits that could run on DC. It's also got circuit breaker protection for different sources of voltage, typically the array and perhaps, like I say, a wind machine. It's got lightning arrestor equipment on it for additional safety. You can see right off that one thing this piece of equipment does is act as a big junction box. It provides a very convenient place to make all of your important connections. Note the size of these connections. This is a power center for a large residential system. This will handle a large amount of power. One of my favorite features of these power centers is that they're so nicely labeled. It's very convenient for homeowners as well as for installing dealers to work on this. This type of labeling is not only required by code, it's a good idea, and it really makes systems go together much safer, and it allows you to do troubleshooting and maintenance, and is really just an excellent feature to have this sort of labeling on all of your electrical equipment. Residential photovoltaic systems make the most sense. They're most cost effective for applications and for people that are living away from where the utility grid currently serves. Oftentimes the utility needs to charge people thousands of dollars to bring in power, what we call a line extension. It's in these situations that photovoltaics can be cheaper than many other options. Typically, photovoltaic residential systems, home systems, can cost anywhere between $10,000 and $30,000. That's a really broad range because the single most important variable in determining how much a system is going to cost is determining how much electricity people need. And electricity is very much a lifestyle issue. Some people can get by with $10,000 worth of photovoltaics. Other people can barely get by with $30,000 worth of photovoltaics. Photovoltaic systems are expensive. It's an expensive technology. It's come down in cost by a factor of 20 over the last decade. However, for homeowners looking at residential PV systems, the smart thing to do is to use energy efficiency and to use electricity efficiently. That means that we can't run certain appliances electrically. We need to shed those loads to other systems, using solar thermal for solar hot water, using propane for refrigeration, and so forth. There are electric refrigerators on the market, and they work well. The energy efficient ones are appropriate. The very energy efficient ones are appropriate for PV systems. It's always cheaper to invest in efficiency than it is to invest in more solar. It's a supply versus demand side sort of management issue. But nowadays, we've got some wonderful appliances. This light bulb here, the compact fluorescent light bulb, is really the most revolutionary thing we've got, including this wonderful space-age technology. But with this light bulb, it has reduced the effective cost of photovoltaics by a third or a quarter as much, because now we have light bulbs that will put out the same amount of light for a quarter to a third as much energy. That means we can buy a quarter or a third. We only need to buy a quarter or a third of the photovoltaics that we needed to buy before we started using these bulbs. And these bulbs can put out as good, if not better, quality of light than the conventional ones. So efficiency is the answer. The wonderful thing about PV systems is that they're modular, they're expandable, they can be increased in size very conveniently. As people's needs change, and they always do change, as they need more lights, as they need more appliances, as families grow, we can add more panels, we can add more batteries, we can add larger inverters, we can expand the system. It's also true that people may want to get involved with photovoltaic systems and may not have all the necessary capital up front to invest in a large system. It's possible to start with a small system and to add to it as funds become available. In fact, we know people throughout the country that are going off the grid one circuit at a time, we call it, by investing in a few $1,000s in photovoltaics up front, and then a few $1,000s on a regular basis. They can slowly wean themselves off of the power companies. There's no question that the sunnier regions of North America, it's better to use photovoltaics. It's a little cheaper. You need less collector area. That's really what it comes down to. But there's no part of North America that we found that is inappropriate for solar. It's true that in rainy regions, you are going to need more collector area. You're going to need a different type and perhaps style of system. But photovoltaics works everywhere in North America and just about everywhere throughout the world.